Dear students, today we'll see the seventh part of multiple choice questions on semiconductor electronics, which can be asked in competitive exams like NEET, JEE, and CET. So let's start with the questions. Now here in this question, it is asked that the following figure shows a logic gate circuit with two inputs A and B, and the output is Y. The voltage waveforms of A, B, and Y are given in the figure. Now, according to this voltage waveform, the level of the voltages in the waveform, we have to find out which logic gate does this waveforms represent, whether it is NOR gate, OR gate, AND gate, or NAND gate. So here if you see this waveforms, the first waveform is of input A, second waveform is of input B, and the third waveform is of output Y. Now if you see the voltage levels in the first time interval, the voltage level of A is given as logic 0, B is given as logic 0, and the output Y is logic 1. Now if you see the second, the input A is at voltage level logic 0, input B is at voltage level logic 1, and the output Y is at logic 1. If you see the third time interval, the input A is at logic 1, input B is at logic 0, and the output Y is at logic 1. If you see the fourth time interval, the input A is at logic 1, input B is at logic 1, and the output is at logic 0. If all these voltage levels are put in a truth table, that is the format of inputs and outputs, we can see that for input A and input B, what is the output? So if input A is 0 in the first time interval, input B is 0 in the first time interval, the output is high. Similarly, in the second time interval, when input A is 0, input B is 1, output is high. If you see the third time interval, if the input is 1, B is 0, then the output is high. If you see the fourth time interval, input A is 1, input B is 1, and the output is 0. If you resemble this a truth table with the function of any logic gate, then it says that when both the inputs are high, the output is low. When both the inputs are high, the output is low. Otherwise, if any one input is high or if both the inputs are low, the output is high. Now, this relation represents the functioning of a NAND gate. This represents the functioning of a NAND gate. So, out of these four options, option 4 is the right answer, that this voltage waveforms represent the functioning of a NAND gate. That is, the option 4 is the right answer. So here you can see option 4 is the right answer. Now here the question is, symbol representation of 4 logic gates are as given below, and from this logic symbols for OR gate, NOT gate, and NAND gates are respectively in which order. Now if we observe the symbols here, if you see the first symbol is having two inputs. So these are the two inputs, say A, B, and this is the output. Now here we can see a bubble here, and this gate is AND gate with bubble, so it is called as NAND gate. So the first gate is NAND gate. Second gate is having one input and one output with a bubble here, and we know that the gate which has one input and one output with bubble, it is a NOT gate. So the second one is a NOT gate. Third, if you see, it is having two inputs A and B, and the output is Y, and if you see the symbol, it is known as AND gate. And fourth is, again, it is two inputs A and B, the output is Y, and if you see the symbol, it is OR gate. Now order asked in this question is of OR gate, NOT gate, and NAND gate. So out of this, the OR gate is in the fourth number. So here you can see this is OR gate, and then NOT gate is second number. So here you can see NOT gate, and NAND gate is first number. So the order is 4, 2, 1. And if you see the options, now in these options you can see the second option is 4, 2, 1. So here our right answer is 4, 2, 1. So here you can see the second option is the right answer, that is 4, 2, 1. Now here the question is, the circuit, that is the combination of gates shown is equivalent to which gate? Options are OR gate, AND gate, NAND gate, and NOR gate. Now, if you see a combination of circuits here, so here first we have a 2 input NOR gate. So let this inputs be say A and B. Now this is a 2 input NOR gate. Now output of this NOR gate will be A plus B whole bar. Okay. Now after that we have a NAND gate here. Now in this NAND gate, both the inputs are shorted and therefore the input is acting as one input and one output. So it's acting as a NOT gate. So whatever input we give here from the output of NOR gate, that is A plus B whole bar, will become A plus B here. Okay, after that this goes to further the third gate, that is a NOT gate. NOT gate, as we all know, that it is a complementary gate. So output of NOT gate will be again the complementary of its input. So it should be A plus B whole bar. Now when the output is A plus B whole bar for an input of A and B, that is when the inputs are A and B, and if the output is A plus B whole bar, then it is acting as a NOR gate. So out of these options, option 4, that is NOR gate, is the right answer. So here you can see option 4, that is NOR gate, is the right answer. Now here in this question, it is asked a forward bias diode is, and in the options 4 diagrams are shown. Now we have to see in which diagram forward biasing of diode is indicated. Now here the basic condition for forward biasing of diode is, we know that diode is a device which will be having 2 terminals, and the terminal here is known as anode and this terminal is known as cathode. Now we know that for forward biasing of diode, that is when a diode has to be forward biased, in that case anode should be more positive than cathode. Now this anode terminal should be more positive than cathode. Okay. So in that condition only the diode will be forward biased. Now if you see this 4 diagrams, there are voltages shown at the anode and cathode. Now if you observe these voltages, in the first option, the voltage at the anode, so this is anode and this is cathode, the voltage applied at the anode is minus 4 volt and the voltage applied at the cathode is minus 3 volt. So minus 4 volt is less than minus 3 volt. So option 1 is not the answer. In this case, the diode is not forward biased. In the second option, we see the voltage applied at the anode of the diode is 3 volt and the voltage applied at the cathode of the diode is 5 volt. Again, the voltage at the anode is not positive with respect to a cathode voltage. So even this is not a case of forward bias. If you see the third case, the voltage applied at the anode of the diode is minus 2 volt and the voltage applied at the cathode of the diode is plus 2 volt. So minus 2 volt is less than plus 2 volt. Again, here the diode is not forward biased. If you see the fourth option, the voltage applied at the anode is 0 volt and the voltage applied at the cathode of the diode is minus 2 volt. So here we see there is a condition that the voltage applied at anode is 0 volt and the voltage applied at cathode is minus 2 volt and 0 volt is more positive than minus 2 volt. Therefore, this condition says that the diode is forward biased. So here option 4 is the right answer, which indicates that the diode is forward biased. So here you can see option 4 is the right answer. Now here in this question, application of a forward bias to a PN junction, that is when a PN junction is forward biased, what happens? Option 1 is increases the number of donors on the N side, increases the electric field in the depletion zone, increases the potential difference across the depletion zone, and widens the depletion zone. Here we have to see whether the number of donors, that is electrons, are increased or what. We have to see whether the electric field of the depletion region is increasing or what. We have to see whether potential difference of the depletion region is increasing or whether the depletion region is widening. So here if you see, this is the PN junction which is connected in forward bias condition. So here you can see the p-type material here, the p-type semiconductor, where holes are the majority charge carriers, is connected to the positive terminal of the battery, and n-type semiconductor here, whose electrons are majority charge carriers, is connected to negative terminal of the battery. If this is the connection, then the PN junction is in forward bias condition. Now when it is in forward bias condition, the depletion region, which is here, okay, it will have its own electric field and it will also have its own potential. Okay, so this electric field, whenever a forward bias condition is put into, whenever the diode is biased with forward bias condition, the electric field of the depletion region will decrease. Similarly, the potential or difference also is counterattacked and that is also decreased. So both electric field and potential difference of the depletion region will decrease. They are not going to increase. And also the depletion layer region also decreases because of forward bias. Now only thing what is true here is when this negative terminal is connected to N-type semiconductor, and in N-type semiconductor negative charge particles, that is electrons, are majority, so it is helping to induce more electrons. It is helping to induce more electrons, and this is what it is inducing more donors. So the first statement of the option is correct, whereas the second, third and fourth statements are wrong. So here you can see the first option is the right answer. That is, application of a forward bias to a PN junction increases the number of donors on the N side. So here in this question, it is asked, Zener diode is used as, options are option number 1, producing oscillations in an oscillator, option number 2, amplification, option number 3, stabilization, and option number 4, attenuator. Now, if you remember the working of Zener diode was always used in reverse bias condition. And in reverse bias condition, if we observe the graph was like this. Say, if you are speaking about the reverse bias condition, we can draw the graph of the third quadrant where the voltage is negative, or the voltage across the Zener diode is negative, and the current flowing through it also is negative. So here we see that in Zener diode, initially as we increase the reverse bias voltage, the voltage will increase, and then there is a flow of current, and there you can see that there is a sharp breakdown. Now this breakdown says that the voltage across Zener diode, that is the Zener voltage, remains constant and the current varies. So this voltage remains constant. At a particular value. So this feature of Zener diode is very useful to keep the voltage constant. That means it is used in application of stabilization. So Zener diode is primarily used in a very important application of voltage stabilization. So option 3 is the right answer. Zener diode is used as stabilizer or a stabilization. It is used in the process of stabilization. So here you can see Zener diode is used as, option number 3 is the right answer, that is stabilization. Now here in this question it is asked that in semiconductors at room temperature, what happens? Option 1 is the valence band is partially empty and the conduction band is partially filled. Option 2 is the valence band is completely filled and the conduction band is partially filled. Option 3 is the valence band is completely filled, and option 4 is a conduction band is completely empty. Now here this question is related with the energy band diagram. Now if you have seen the energy band diagram for semiconductors, it is drawn like this. This is the energy band diagram. Now here you can draw the valence band. This is the valence band. This you can call it as valence band. And here you can draw the conduction band, a conduction band. Now the forbidden energy gap between the two bands, this is forbidden energy gap. It is of 1.1 electron volt for semiconductors. Okay. Now, all the valence electrons, that is, whenever you see an atomic structure, say this is your atomic structure, this is nucleus with protons and neutrons, and around the nucleus you are having orbits, and in this orbits you have electrons revolving. Now, if you have the electrons in the outermost orbit of any atom, those electrons will be called as valence electrons. So here if you can have this outermost orbit electrons, these electrons will be called as valence electrons. Now, if you have many such atoms together in a crystalline structure, all these valence electrons will be having their associated energy. Now, all that energy of all those atoms together will constitute with can be shown as a valence band. So, in this valence band, whatever we have shown in this energy band diagram, we can say that this energy band diagram is having all these valence electrons, all these valence electrons of all the atoms together. Okay, so all these valence electrons are shown in the valence band. Now, at a room temperature, what will happen? Because of a certain heat produced at room temperature, some of these valence electrons can come out of the atomic structure because they are loosely attached, they are not so tightly attached with the nucleus. They can come out. So some of the valence electrons will come out and they become free electrons. Now, all such free electrons of all the atoms together in that particular crystalline structure will constitute the conduction band. All that energy associated with all those free electrons will be your conduction band. That means if you see this energy band diagram, we can say that at room temperature, few of these electrons, some of these electrons from valence band will come to conduction band. Now, because of this, if you see this scenario at room temperature, the valence band which was completely filled with electrons has let go some electrons to the conduction band because of the room temperature heat. Okay, that means valence band was originally filled. Now it is partially empty. Now this is partially empty. Valence band is partially empty. Similarly, the conduction band was empty. Now it is partially filled because some electrons have come here. This is partially filled. Conduction band is partially filled. That means out of these four options, the first option, if you see, the valence band is partially empty and the conduction band is partially filled, is the correct option. So for this question, in semiconductors at room temperature, what happens? Then option 1, that is valence band is partially empty and the conduction band is partially filled, is the right answer. So here you can see option 1 is the right answer. Now here it is asked that in good conductors of electricity, the type of bonding that exists is which one? Options are metallic bonding, van der Waals bonding, ionic bonding, and covalent bonding. Now if you remember the crystalline structure of a metal, then we know that metals are made up of positive ions. They are made up of positive ions which are very closely packed together. Now these positive ions are surrounded by mobile electrons which can move. They are attached to their origin atom, but they can move. They are movable electrons. Okay, now these are your valence electrons which can move. Now these electrons can come out. Now one of these electrons, if it comes out, another electron will take its place. Now this concept makes the metal structure, the metallic structure, intact. Okay, now movement of these electrons will make the flow of electric current, and that is why we say in metals there are excess of electrons which allow flow of electric current very easily. Now in this concept, there is a force, there is an attraction force between these metal ions and the free electrons. The positive ions, what we show, and the free electrons, what are there surrounding it, which is also called a sea of electrons. Now this electrostatic force, this electrostatic attraction what you have between the metal ions, the positive ions, and the free floating electrons is known as metallic bonding. This is known as metallic bonding. Now, therefore, in this question, in good conductors of electricity, the type of bonding that exists is which one? Then option 1 is the right answer. That is the metallic bonding. So option 1 is the right answer. So here you can see option 1, metallic bonding, is the correct answer. Now here in this question it is asked that in an insulator, the forbidden energy gap between the valence band and conduction band is of the order of, options are 1 mega electron volt, 0.1 mega electron volt, 1 electron volt and 5 electron volt. Now if we remember the definition for insulators, we know that insulators are those substances which do not allow the passage of electric current through them. That means there will be no free electrons flowing through it. Like for examples, materials like wood, glass, plastic, etc. Now, no free electrons to form the electric current means all the electrons will remain in valence band only. So the valence band will be full and the conduction band will be empty. Like if you remember the energy band diagram for insulator, we can show like this. So here we can have our valence band, that is the energy associated with all the valence electrons of the atoms. So here will be valence band and this will be full of electrons. This will be full of electrons. So no valence electrons will become so easily free. So this is your valence band. Valence band. Now, because it is difficult for a valence electron to become free so easily, a conduction band is shown little far in case of energy band diagram for insulator. So this is your a conduction band. Now we know that a conduction band is a band which is having energy associated with all the free electrons. Now here in insulator, it is very difficult for valence electrons to become free. They require a very high electric field if they have to be pushed from valence electron to conduction band. Therefore, the forbidden energy gap is large in insulator as compared to conductor and semiconductor. So out of these options, option number 4, that is 5 electron, will be the right answer, which shows that the forbidden energy gap is very large. Therefore, we require a very high electric field if we have to push the valence electrons from valence band to conduction band. Therefore, out of these 4 options, option number 4 is the right answer. That is 5 electron volt is the right answer. So here you can see for an insulator, the forbidden energy gap between the valence band and conduction band is of the order of 5 electron volt. So here it is asked that in a reverse biased PN junction, when the applied bias voltage is equal to the breakdown voltage, what happens? Options are option 1, current remains constant while voltage increases sharply. Option 2, voltage remains constant while current increases sharply. Option 3, current and voltage increases. And option 4, current and voltage decreases. Now, as we are speaking about reverse bias PN junction, we should be very clear with the concept of minority charge carriers. Now, we know that in an intrinsic semiconductor, that is pure semiconductor, if it is having sufficient thermal energy, if the temperature increases, if there is sufficient thermal energy, some of the valence electrons will jump into conduction band. That means valence electrons become free electrons. And these free electrons will be called as minority charge carriers. And whenever there is a free electron put into the conduction band, there is one hole left in the valence band. This will create electron hole pairs. Now this concept of minority charge carrier is very important to understand reverse bias concept. Now if you see a diagram of a reverse bias, we can see here in a reverse bias condition, we know that the voltage applied here will be such that the negative of the battery is connected to the p-type semiconductor and the positive of the battery is connected to the n-type semiconductor. Now this is going to attract the majority charge carriers back towards the battery. That means in p-type the holes are majority charge carriers. These are attracted over here because holes are positive charge particles, and even in n-type electrons are negative charge particles, they will be attracted here, and the depletion layer is increased. The depletion layer in between is increased. Now if you remember the minority charge carriers, now minority charge carriers, that means in p-type semiconductor, electrons are minority charge carriers. So here you can show some electrons which are minority charge carriers, which are negative charge particles. Similarly, in n-type semiconductor, holes will be minority charge carriers, which will be positive charge particles. Now here, if you see this supply here, a battery supply, the negative of the battery now is going to have an impact on the electrons, which are the minority charge carriers of p-type semiconductor, and positive of the battery is having the impact on holes, which are minority charge carriers of the n-type semiconductor. Now for these minority charge carriers, this type of battery arrangement is acting like forward bias, so putting a force on it to cross the depletion region. Now initially when the voltage is increased, when the applied voltage is increased, very few minority charge carriers are able to cross the depletion region. Now here we see that if a reverse voltage is increased continuously, the kinetic energy of the minority charge carriers becomes high enough to knock out these electrons from the semiconductor atom, so that these electrons become free electrons and they come out and join the flow of current. So here at this stage, when the reverse voltage reaches the breakdown voltage, we see that there are sufficient minority charge carriers which are forming a large amount of current to flow. So here you can see a large amount of current is going to flow because of minority charge carriers at a breakdown voltage which remains constant. That means the voltage applied is remaining constant, whereas the current which is flowing is increasing. So therefore, out of these options, option number 2 will be the right answer, which says that in a reverse bias PN junction, when the applied bias voltage is equal to the breakdown voltage, the voltage remains constant while the current increases sharply.